So this is the third part of the interesting topic of polynuclear aromatic hydrocarbons. So we have in the first two parts we have seen the general introduction about the polynuclear aromatic hydrocarbon, also called as PAH, and also we have seen different the structural aspects of this the class of these hydrocarbons. We have seen the isolated PAH. We have also seen the fused one, right? The example is naphthalene. And for the isolated case, we have seen also how to prepare the method of preparation of this PAH and also their chemical reactivity. Now it will react with some chemicals like nitration or halogenation reaction. And the later part we have seen the naphthalene as an example for the fused PAH and their structural aspect and their aromatic properties and also the physical and some chemical the properties and how we can obtain naphthalene from the natural resources from like coal or petroleum. So now we will see in this class today we will see about the synthesis of naphthalene from the laboratory and their important electrophilic reactions. So let's move on to this topic and see how it can prepare in the laboratory. This is the third synthesis of naphthalene under the method of preparation of naphthalene section. So importantly, our synthesis is the important synthetic scheme necessary for preparing naphthalene in chemical laboratory, right? So this is I have already told in the last class. This is very important for making the naphthalene in lab because if you obtain from the coal or from petroleum, then we can of course obtain naphthalene, but it is a very cumbersome process, right? It's a difficult process. And also petroleum and coal are natural resources. It can deplete. So we need uh, we need a laboratory synthesis for the naphthalene. So before we can prepare in bulk and use for the necessary whatever necessary needed, like preparation of drugs and some preparation of some useful chemical compounds. So, however, this scientist he prepared naphthalene in laboratory using this following scheme. So, first what he took is he took benzene. So, benzene is a very simplest aromatic hydrocarbon, right? He took benzene and react with succinic anhydride. Okay, succinic anhydride and using this AlCl3 as a catalyst. And he got the beta benzoyl propanonic acid as the product. Then this beta proponic benzyl propanonic acid undergo Clemmensen reduction. Clemmensen reduction is nothing but reduction is addition of hydrogen, right, or loss of oxygen. So Clemmensen reduction. So if you take the benzoyl chloride and add hydrogen or some zinc, right, as a catalyst, zinc amalgam, it will reduce. It will add hydrogen to that, and you will get it. And what he got is gamma phenyl butyric acid is the product, which upon on heating with sulfuric acid, so if you add some sulfuric acid and heat it, you get this tetralone as the product. Then tetralone, that is alpha tetralone, on reduction, same Clemmensen reduction, and then treatment with selenium gives naphthalene. So the reduction meaning we are adding hydrogen, right? The same Clemmensen reduction. And treatment with selenium is a cyclizing agent. The aromatizing agent, meaning it will remove hydrogen and it will aromatize. They will get all the double bonds. And aromatic meaning it is having a delocalized double bond, right? So this will help in to make the aromatic character in that any compound. Selenium. We'll see in detail. So these are the steps needed for prepare naphthalene. So you can see preparation of naphthalene is not easy and it involves multi-step process, right? First prepare this one, second this one, second third this one, and lot of treatment also needed. So we will see in detail this chemical steps using chemical synthetic scheme. In the next slide, you can see here. This is again this our synthesis. Now I am draw all the chemicals in this scheme. So benzene, I told that first step we needed benzene treated with succinic anhydride, this one. So if you take both in the presence of AlCl3, you will get beta benzoyl propanic acid, right? You will get this one. So meaning a benzene ring attached with CO. So this CO, CH2, so this CH2, CH2, CO, and this ring will open, so you will get an acid. Okay, OH. This hydrogen is coming from here. This hydrogen here, that will attach here. Okay, so you get this one. There is this structure is called as, this compound is called as beta benzoyl propanic acid. On treatment with zinc amalgam and HCl, you will get the gamma phenyl butyric acid. This one. So as I said, there is a reduction reaction. It's a Clemmensen reduction reaction. If you add this oxygen will go away, right? You remove the oxygen and add hydrogen. This 2 hydrogen is added here. Okay, 1 oxygen is removed. You can calculate the molecular formula and check how many hydrogens are added and how many oxygens are removed. So this is a reduction reaction. Remember this. What will happen next? This undergo reaction with concentrated H2SO4. So if we add the acid, it will cyclize, right? This hydrogen will come here and then the water will remove and this will attach here. So this is how we get this compound, this alpha tetralone, which again undergo the same reduction reaction. So this is a zinc amalgam and HCl here. You can see here, and this again meaning that the oxygen is removed and hydrogen is added here and get this compound, and which on reaction with selenium or which on treatment with selenium, it will aromatize. That's what I said. Then you get the 2 double bonds here. So it will remove some hydrogen. So we remove hydrogen, double bond will be created automatically, right? So this is how we get the naphthalene. So naphthalene involves multi-step process. First step involves synthesis, formation of beta benzoyl propionic acid, and then next it will form the gamma butyric butyric acid, then alpha tetralone, and then finally you get the naphthalene. So this is how we can prepare naphthalene from benzene and succinic acid. Okay. So with this, we will next want to see how the naphthalene reaction, the reactions of naphthalene. The important reaction naphthalene undergo, what we can see here in this is the electrophilic substitution reaction. So we have already seen what is electrophilic substitution reaction in the benzene chapter and also in the phenol chapter, right? The electrophilic substitution meaning electrophilic is a positive species and the electrophilic substitution meaning this positive species or positive chemical species attach on the naphthalene ring. This is the substitution. So substitution meaning is it will remove the hydrogen. In the place of hydrogen, this new electrophile or this positive charge species will attach. We can see in the scheme, we will clearly understand. So naphthalene undergo electrophilic substitution reaction preferentially at C1 position. So we already know that how to number the numbering scheme of the naphthalene, right? Which one is the first carbon, second carbon. So in electrophilic substitution reaction undergo at the C1 position. C1 position attacks leads to more resonance structure compared to C2 attack. Compared to the C2 position. This is a very important point to note. So see in the first here I mentioned that electrophilic substitution reaction on naphthalene undergoes at the C1 position. Why? Because you can see if you attach the electrophile at the C1 position, we can write more resonance structure. We already know that if you can able to write more resonance structure, the stability of that intermediate will be more, right? So more resonance structure meaning more stable. This you can remember. So C1 position attack leads to more resonance structure. This means more stable this position attack. So it will prefer the C1 position compared to C2. The next one I will show you what are the structures when attacked at the C1 position by an electrophile and how many structure or what is the structure obtained when we when the electrophile react at the C2 position. Then we can know that how many resonance structure are possible and why the C1 is preferred. So now let's see. Here I have shown or depicted the naphthalene structure with the number scheme, right? This is a number 1 and this is number 2. So this way, this is C1, this is C1 position, this carbon is numbered as C1, and this is a C2 position, this carbon is numbered as C2. Now let's move on to see how the electrophilic reaction occur in this C1 position and C2 position, and what are the resonance structure possible. So this is electrophilic substitution reaction, and here first I want to show you how the attack happens at the C1 position. Attack at C1. So meaning here, right? So this is an electrophile, that is a positive species. Example of electrophiles are nitro, NO2 plus, Cl plus, bromine plus, Br plus, CH3CO plus, CH3 plus. So these are the examples. This all we have covered in the unit 1, that is benzene chapter. Okay, this is a electropositive species, E plus, and this is a naphthalene, and there is attack from here to here. So this is shown in this red arrow, this attack. And what you will get is 2 resonance structures. We will get it. This is the first resonance structure, okay, and this is the second resonance structure. So in the first resonance structure, you can see that, when they attack, this double bond becomes go here and attach. This double bond will go here and attach with the E plus. So there is a double bond is removed here. Okay, and this double bond went here. So it's a positive charge will come automatically. Because carbon is having only 3 bonds here, 1, 2, and then hydrogen. Automatically a positive charge will come. Because this double bonds are having 2 electrons, so these are gone. If you remove electron, it will be a positive charge, right? We already know that each double bond is made of 2 electrons. So you will get a positive charge here. So how can we write a second resonance structure? This bond can travel here, so there is a positive charge. Automatically the electron will want to go to the positive charge, because this positive charge needed electron. So it will automatically suck this electron, this double bond here. So it will transfer, it will go here, right? So it will goes here, and this positive charge automatically comes this carbon to this carbon. So there are 2 resonance structure possible. One, carbocation, that is carbon having a positive species, carbocation present here, or the second structure, carbocation goes here. The 2 resonance structures are possible. Now let's see how the attack happens at the C2 position. So this will be interesting, because if you attack the electrophile with this same double bond, right? But in this case, the new bond will form here. I will show you. So attack here, and then you will get one resonance structure only. So the new bonds formed here. You can see this is here, it is here, this carbon 1, this is carbon 2. And the positive charge is here. Now this bond can move here? No. Because it has to move here and then here. It cannot move here, because then it will become carbon having 5 bonds here, this carbon. So it cannot move here, right? Because positive charge is far away, it cannot move here. So it's having only one structure is possible for this ring. Okay. It can also move from here to here, that is possible. But I am telling only about this ring. This ring, there are 2 structures are possible. One is here, one is here. But here I was having only one possibility. It is only positive charge is only the one resonance structure. What is the meaning? The C1 attack is more favorable compared to C2 attack. C1 attack is more favorable than C2 attack. So the electrophile will goes here only. Okay. We will see some example. We will see nitration reaction, we will see halogenation reaction, sulfonation reaction, and see where the electrophile is going. Now let's see for nitration. When there is a nitration, where it will go? Automatically it will go here, right? First position. We will see that. So this is some electrophilic substitution reaction examples of naphthalene, and first we will see the nitration reaction. So naphthalene reacts with concentrated nitric acid in the presence of concentrated sulfuric acid. This is concentrated nitric acid, this is concentrated sulfuric acid, this is a catalyst, and this is naphthalene. What you will get is 1 nitronaphthalene. This is what I said. The final product you will get is 1 nitronaphthalene, because this is the intermediate, right? This is intermediate. You can see that electrophile is attacked here in the first position. So you will get 2 resonance structures. The C1 attack is more favorable. So you will get this 1 nitronaphthalene as a product. You won't get the 2 nitronaphthalene. Okay, you won't get 2 nitronaphthalene. You get only 1 nitronaphthalene, because this is more stable compared to the 2 nitronaphthalene. during the reaction, right? During the reaction, this is more stable because there are two resonance structure is possible here compared to this one. So we will get only one nitronaphthalene as a product. So naphthalene plus concentrated nitric acid plus in the presence of concentrated sulfuric acid, you get one nitronaphthalene. What about this sulfonation reaction? Sulfonation reaction is very interesting because you will get both products, depends on the condition. So this is a very interesting one because you see the naphthalene reacts with concentrated nitric sulfuric acid at 40 degrees Celsius to give naphthalene 1 sulfonic acid as the product. This is the product. Naphthalene 1 sulfonic acid. So take the naphthalene and add sulfuric acid at 40 degrees Celsius. You will get one naphthalene 1 sulfonic acid. I said we can also get 2 sulfonic acid in this case. Okay, and I will tell you why we will get 2 sulfonic acid as a product. Why that is also forming. So if we change the reaction condition, let's say if we eat more, if we give more supply, more heat. Okay, so naphthalene plus concentrated sulfuric acid, we heat it at 180 degrees Celsius. So if we heat it a little bit more, high temperature is needed, you will get naphthalene 2 sulfonic acid. So this is very interesting. But in the case, see, in the mechanism section, I told C1 attack is more favorable. So we'll get the product will be here only, the 1. C2 attack is not favorable because of the less resonance structure. But why we are getting this in the case of sulfonic acid? Why we are getting the 2 naphthalene 2 sulfonic acid as a product? Why the substitution here? So let's see why naphthalene 2 sulfonic acid formed, right? We can raise this question. So this is the naphthalene 1 sulfonic acid, and if you look carefully, I also put the hydrogen. Okay, so each carbon is having one hydrogen. Especially this hydrogen is very important because this is straight, right? This is straight, and sulfonic acid group also straight. You see, this is straight and this is also straight, and there is an interaction because this is very close. And sulfonic acid is a big group, right? It is having S, O, and H. So there are 5 different groups are there. 5 groups, 5 atoms are there. 1 a sulfur, 3 oxygen, 4, and 1 hydrogen 5. So total 5. This can have an interaction, right? So always remember, always less energy or less interaction is more stable. Less energy of a molecule or less interaction. Less interaction means automatically meaning is less energy. That is more stable. So naphthalene 1 sulfonic acid is having an interaction, direct interaction between the hydrogen of this ring with the hydrogen with the sulfonic acid of this one. Or you can say that first position is having an interaction with the 8th position. Right? This is the 8th position. 8th position added. This one. So there is a steric hindrance, meaning steric hindrance means there is a crowd, there is an interaction, hindrance. In the case of naphthalene 1 sulfonic acid. What about the naphthalene 2 sulfonic acid? Let's see. Naphthalene, this is the structure of naphthalene 2 sulfonic acid, and we can see here the sulfonic acid group is far away from this hydrogen. Okay, this is far away from this hydrogen. This hydrogen is not straight, this hydrogen will be here. So there is not much interaction. This hydrogen will be here. I did not put it, but you can imagine there is an angle is there. Sulfonic acid group is hydrogen is here for this one, I am telling. For this carbon. Okay, the sulfonic acid is here, this carbon like this, and for this carbon the sulfonic acid will be like this. There is an angle, so there is no direct interaction, there will be like this. Same thing here, this sulfonic acid is here and this hydrogen is here. So there is no direct interaction for this hydrogens, and this hydrogen is far away. This is the straight one that is far away. So this is having no steric interaction, no interaction, no overlap between these two. So what is the meaning? This is more stable. This is more stable compared to the naphthalene 1 sulfonic acid. Because of this reason, for sulfonic acid case, 2 sulfonic acid is possible. But for some small group, so this I told, this is sulfonic acid having a many 5 atoms. But for small group like chloro, bromo, even nitro, there is not much interaction between the hydrogen of this hydrogen and this other group like chloro. We will see that in the next class. Why the nitro is preferred in the first? Because there is not much interaction compared with the sulfonic acid. This is why In the case of sulfonic acid, we can also it is also easy to prepare the 2-nitro-naphthalene 2-sulfonic acid, right? In the case of sulfonation reaction. So far we have seen the laboratory synthesis of naphthalene and also the chemical reactivity, that is especially the electrophilic substitution reaction of naphthalene. We have seen some examples like nitration and sulfonation, and we also now know why the electrophilic substitution reaction occurs at the first position. Okay, because of the resonance structure. Remember that because of the more resonance structure we will get in the C1 attack. But in case of sulfonic acid, it is also possible to prepare. So I will show you this one, naphthalene 2-sulfonic acid, because of the steric entrance. Okay, no steric entrance here, so it is preferred compared to the first one. So this is so in the next class we will see more about the reactions of naphthalene, and also we then move on to see the 3-ring system, fused 3-ring system, like anthracene and phenanthrene. So this is for this class, and I will see you in the next class. Thank you.